let's take a look at our plan. Rihanna said that if I told her there was a test today, she would cry. Good thing that there's not a test today, but there is one tomorrow. So we need to know kind of what's on it. My plan for the day is to give you that outline of what's going to be on the test, what the test might look like. I don't have it finalized, but I have started it, and I can give you kind of a sense of what's going to be on it. My goal is to write it for the period, right? That's always my goal, and I'm going to shoot for that. So what I'm going to tell you may change depending on kind of what goes on there. Anyway, after that, rats, I have to go grab something. We're going to do some energy bar chart practice, and then I've got one kind of big problem for you to work if for whatever amount of time we have at the end. Okay? So at this point in the unit, you know everything that you need to know. Like there's no new material for you to learn, but there is some, like mastering of it and kind of, polishing off the rough edges and stuff like that. So let's take a look at the list. I just kind of went through the calendar and looked at what we've covered. So here you go. This is what we've done. We talked about types of energy: kinetic, gravitational potential, spring potential, and thermal, or heat energy, friction energy, whatever you want to call that. We've talked about the fact that in a closed system, that means that there are no external forces, that energy must be conserved. That means that anytime that you write out a problem, you're going to say something to the effect of the total energy at the beginning has to equal the total energy at the end, right? Yeah.
Can I take a picture of this?
Yeah, and I can post it on Canvas as well. Yeah. Somebody send me an email and remind me so I don't forget, because otherwise I will. But yes, absolutely. You can take a picture of it if you'd like. Work done occurs when there's an outside force acting, right? So if there's no outside force, energy has to be the same. If there is an outside force, that means that work is done. Work being done means that there is going to be a change in energy of the system. Okay? Kind of two different ways to define that. Work is change in energy, or work is the force times the distance, also known as the area under the curve. Okay? And then we've got power, which is work per time. All you need to remember there is that you're going to take that work or that change in energy and divide it by time. Okay? Look at the units. A lot of times people get really, really intimidated by power problems. If you look at the units, and if you do, what the heck is that called? I just lost it. Unit cancellation, that's not the nice word for it, but when you do that, you can solve most power questions. The other things that we kind of talked about, we talked about Hooke's law. That was kind of a piece of getting us to spring potential energy. We talked about energy bar charts a little bit. We're going to talk about those a little bit more today because I think that they're important, and I don't feel like I covered them as well as I hope to. And then also energy diagrams, like if you have that energy over distance graph and you kind of the little curvy graphs, those are important too. I don't think that there is going to be an energy diagram on this test, but they're good to know. Okay? Questions about any of that? Things that you're like, I don't really think we talked about that, Ms. Carveling, or anything like that? Hopefully. Yeah, go ahead.
Is the energy diagram the graph?
The curvy graphs where, the potential can't go above the line, that stuff. Yeah. And then the bar charts are the ones where we're counting up bars, and we're going to do some more of that today. Yeah. Other clarifications or questions, things like that? My first round of kind of sketching out the test is done. Like I said, that it's not finalized, so there is room for change, but my guess as to what you might expect on the test would be something like 4 or 5 multiple choice questions. There will very likely be an energy bar chart question, okay? One, what I call conflicting viewpoints. That's where, Bob says this and Alice says this and Joe says this, and you have to tell me who's right and who's wrong, okay? And why. The why part's the most important part. And then 1 or 2 problems. So some amalgamation of that. If it had all of that, it would be too long, and I am aware of that. But that's kind of what I am working and choosing from at this point. Okay? Question?
Do you expect the multiple choice to have ones that were given in class where they provide an explanation for why it's things?
I haven't decided. Probably not, just because that takes a lot of time. But if I decide to cut a bunch of other stuff, then maybe. Because I think that that's an important process for you to go through. You know what I mean? Yeah. I have not decided yet. Question?
What do you mean conflicting viewpoints? It's like what she just explained.
What do I mean? Somebody help out me, please.
So like if there's like a problem and then like a couple of students will give their like opinions on it or like their answers to it, and you have to say which one you think is right and why.
Does that make sense? It's okay. It's all good. All right.
Didn't regular physics kids have one of their tests?
They did on their test that they just took, in fact.
They were arguing about it.
Yeah, it's okay. That's good. That's good. That means that they're like, I don't know, engaging with it or something. All right. How are we doing here, team? Are we okay? Besides Nick, I'm just going to ignore your responses.
You're supposed to talk about momentum.
Oh, yeah, I took that one off. Well, I shouldn't say that. There were two of them. I took one of them off. So Courtney reminded me because I started looking at this, like kind of looking at old tests yesterday. And I told Courtney to remind me, and she's reminding me now, that old stuff does not go away, right? So in some classes, and I don't mean that as a threat at all. I just want you to be aware, okay, that all of the, like everything we've done technically is free game, like fair game. I don't have any free body diagrams on there, okay? The one thing that I would strongly recommend that you just know a definition of is momentum. It's not like a, collisions problem, but make sure that you know what momentum is. Okay? And you have your equation sheet there too. So it's not like you can't be like, momentum starts with a P and it's right there and there you go. Right? Yeah. Okay. Issues, questions, concerns right this moment.
Can you scroll up a little bit?
Oh my gosh.
Take a picture.
All right.
Whoa. No. Mr. Butler.
So hopefully you have had a moment to give this a shot. My OneNote is, there we go. Now it's okay now. All right. Is back and maybe ready to go. We'll see. All right, there we go. All right. So if you have finished this, great. If you haven't, let's talk about it. It says the velocity of a tugboat changes from 2 meters per second west to 40 meters. Friends, could you please be quiet so that I can hear myself talking and others can as well? 2 meters per second west to 4 meters per second west while a force is applied for 20 seconds. So let's just think about this from the big picture beginning. Henry, put the scissors down. Thank you. We don't play with scissors, friends. That's not what we do, okay? Does the boat have kinetic energy at the beginning?
Yes.
Does the boat have kinetic energy at the end?
Yes.
Is it the same amount?
No.
Which means that what must have happened? Boom. Okay, so that's the easy board. That's the easy story. Now we do need to color this in, and not only do we need to color it in, but we also need to say that the bar heights should be in correct proportion to one another. That's one of the keys here. That's the thing we have to think about. So you get to pick, right? This is like a choose your own adventure story of drawing pictures. We get to pick how many bars of kinetic energy we start with. Two is what I'm hearing from a couple of people. So you can just pick one. So one of the small ones. So there are enough for everything. So there are 2 small ones and 3 big ones or something like that. Yeah. 4? Something, I don't know, whatever. All right, so there are 2 bars of kinetic energy at the beginning. How much kinetic energy do we have at the end then? I hear 8. Wow, where in the world does that come from?
Because you doubled the kinetic, or no, that's wrong.
You doubled the velocity.
That means that it's increased by a factor of 4.
Does that make sense? Is everybody? We've done this a bunch of times now, and I want to make sure we're okay. Yeah. Okay. So we got 2 here. So we're gonna have how many then? You said 8. 1, 2, 3, 4, 5, 6, 7, 8. Did I count that right? I think so. Sweet. And then, easy peasy, we got this. How much work has been done? 6 bars, right? 1, 2, 3, 4, 5, 6. Life is good?
Life is great.
Fantastic. Let's do another one. All right, here's another one. It's very similar, but not exactly the same. The velocity of a tugboat changes from 4 meters per second west to 2 meters per second west while a force applied to the tugboat over 20 seconds. Pretty darn similar, right? But a little something has changed. Complete the work and energy kinetic bar chart for this process. What's different? It's slowing down. So that means that we're going to start with how many bars of kinetic energy? 8. Or we could pick as many as we want, right? It doesn't matter. You could start with 4 and then go down to 1. That would be okay too. It doesn't matter, but they were loud when they were saying 8, so I'm going to do it that way so that they don't get mad. So this is on your second one. And if you want to write yourself a little note, right, boat speeding up, boat slowing down, so that you look at these tonight and you're like, oh, yeah, that's what we did. That's totally fine. You are getting confused? No, but on your other piece on the back, maybe? There you go. Yep. See, what was supposed to happen is they were all supposed to fit on one side.
No, which one is?
It doesn't matter.
No, the first one. This is the boat speeding up.
So the first one was the boat speeding up, right? Because work is being done. All right. We've got 8 bars of kinetic energy to start. How many bars of kinetic energy do we have at the end?
2.
Just 2. So now, if we don't have the same amount of energy at the beginning and the end, what does that mean? Means that work's been done. In this case, because it's gone down, it means that there is negative work being done. We have kind of mentioned this idea of negative work, but we haven't really defined it before. 1, 2, 3, 4, 5, 6. So I want to make sure that this makes sense to you. Let's write down a couple of ideas here. So work is equal to the change in energy. In this case, it's kinetic. So if energy is changed, that means work is done. Remember, we also said that work was equal to the force times the distance, where the force and the distance are parallel to one another. Okay? The piece of that we really didn't talk about is if they're anti-parallel. If instead of the force and the displacement being in the same direction, if one's pulling the other way, okay, then you're doing negative work. So if you think about this, if the boat was going fast and then it slows down, which direction is the force pushing in?
The opposite.
It's pushing this way, right? So if we were going to draw the picture, right, the force is going in this direction while the distance is going in this direction. So really, the angle there, the theta, is 180 degrees. They're 180 degrees off, okay? Which means that the work will be negative, okay? So you might just want to make a note there or in your notes or something like that. If F and D are, we could call it anti-parallel. They are pointing 180 degrees different or opposite directions. What you could say that too. In all of those cases, the work is negative. Okay? Because the force is in the opposite direction. How are we doing? Great? Still happy? Still smiling? All right. We're going to go to the big ones if you're ready, but tell me if, here, I'll take a drink of water and then tell me if you're ready. Sorry, I'm just trying to get through all this stuff. All right, let's find one of the big ones. So the reason that these ones are big is because they've got more kinds of energy, right? The first two that we did just had kinetic and working kinetic. And you'll have to excuse this book because the book that these come from, instead of using U, they use PE, right? Instead of using K, they use KE. But you're flexible people and you can handle it. I know you can. So we got kinetic, we got gravitational potential. We're putting spring energy in there. The only thing we're missing is thermal energy. Now, that's kind of interesting. One thing to keep in mind is that often, so work can be an applied force over a distance. Thermal energy is often not included, and it is work that is being done on or by a system. So I just wanted to point that out to you as well, that sometimes we include thermal energy and we make our system big enough to include that, but a lot of times we don't, and that friction instead is lost energy, or it's work being done taking energy out of the system. So just kind of keeping that in your head. All right, so here's the situation in this story. We've got a block that's pushed so that it moves up a smooth, frictionless surface, okay, at a constant speed from A to B. It says to complete the energy bar chart for the Earth block system as the block moves from point A to point B. Put the 0 point for the gravitational potential energy at A. So they're taking that opportunity away from you, but that also means that we all can have the same story. So I'm going to go ahead and draw my H equals 0 line down here. Okay? And given that information, let's talk about the beginning part of the story. Does the Earth block system have kinetic energy at the beginning of the story?
Yes. Yes.
Sure.
It's yes or no. It's one of the two. Somebody give me evidence that it is yes or no.
There's the little dashing lines. It's moving.
The picture looks like it is. Are there any words up there that tell us that it is?
Push.
Is put
Constant
is
speed.
push.
Constant speed? Constant speed means it's moving, right? Constant speed means it's moving. So that means we've got some kinetic energy. How many bars of kinetic energy do we want to have?
Half.
Razan, how many bars of kinetic energy do you want? 4, she says. All right. Seems like a reasonable number as opposed to all. All right, we got 4 bars of kinetic energy. At point A, at the beginning of the story, is there any gravitational potential energy?
No.
It's either yes or no. Give me some evidence for one of the two.
No, because it's at 0.
H equals 0?
Oh yeah.
Yeah, so MGH, right? M times G times 0. So that's at 0. I would encourage you strongly to mark that that's 0. Don't just leave it blank. Leaving it blank implies you don't have any idea. Assert yourself. Is there any spring potential energy?
No.
No, there isn't any spring potential. There's no spring in the story. All right. All right, I'm going to skip the work part for right now.
Okay.
Let's talk about the kinetic energy at the end. Does the box have kinetic energy at the end?
Yes.
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 What evidence do you have that it does have kinetic energy?
It's constant speed.
Constant speed. So not only do we know that it has kinetic energy, how much does it have if it had 4 at the beginning?
4 at the end.
It's got to have 4 at the end, right? 1, 2, 3, 4. Is there any gravitational potential energy at the end?
Yes.
Yes.
Yeah. Now, are there any numbers that tell us exactly how much?
No.
There aren't. So that means that we can ask anybody, and I'm going to ask Rihanna, how many bars of gravitational potential energy are there at the end? 3, she says. So we're going to put 3 bars of gravitational potential energy here. Okay. Is there any spring potential energy at the end? No, because there's no spring in the story. That's silly. All right. Last part, that middle part. I have 4 bars of energy at the beginning. I have 7 bars of energy at the end. I've obviously done some work as I have applied a force over a distance. How many bars of work have I done? 3. Why 3, Kate? 7 minus 4 is 3. Duh. Yeah, exactly. You got it. You got it. How we doing? Okay. Anybody want me to not keep moving? That was a lot of negatives in there. I don't know. I'm just going to keep going. Oh.
No, sorry.
No, you're okay. No need to apologize.
So
You got it. Makes sense.
this. I
I
don't know
don't
what I'm
understand.
gonna ask actually.
Do you want to hold on to it and ask me in a minute as it comes to you?
Sure.
Okay.
Yeah, we can keep.
Okay. I've got 2 more of these.
Yeah.
I think. Yeah. All right. A new situation. I'm going to make this one a little bit bigger so you can see it a little bit better. All right. Here we go. A 100 Newton box is initially 1 meter above the ground while moving upward at 10 meters per second. That's a lot of information. Okay. A student starts applying a vertical force of 120 newtons to the box upward with her hand at that point. Says to complete the energy bar chart for the Earth box system before and after the box has moved upward a distance of 1 meter, put the 0 point for the gravitational potential energy at the surface of the ground. Ooh, there's a lot in here. Okay, so here's the ground. 1 meter above this. And then we're going to lift it up a meter from there. So the gravitational potential energy at the beginning, I guess we do know a lot of information here, so we can really do this. Let's see. Oh, there's a lot of information over here. Okay. We got to figure out. So each of these is going to be 100 joules, it looks like. Each of those little blocks is going to be 100 joules. It's a little more mathy than we're used to, but that's okay. So how much gravitational potential energy, well, pass me back up. Does the box have gravitational potential energy at the beginning of the story?
Yep.
How much does it have? Let's use G as 10. Okay, let's make it easy. Okay.
10. Yeah, 10.
So it's MGH, right?
Yeah.
So U sub G is MGH. What is MG in this one?
That's the weight. We have the weight. We don't have the mass. Yeah,
What is the weight?
10. Wait, no. Yeah. 100. No, what that's the weight.
That's the weight, which is what you just said.
Wait, what?
Which is also yes, because
Oh,
to get in,
yeah.
you have to do mass times gravity.
100, yeah.
Oh, darn it.
Are we okay? So the weight is 100 newtons. We're multiplying that by 1 meter because it's got that much potential energy at the beginning. 100 times 1, I got that one in my head, no problem. 100. So how many bars of potential energy gravitational do we have?
1.
Just 1. How much spring potential energy do we have?
0.
Okay. All right. Let's skip the work part for right now. Let's do the spring potential energy at the end first, because that was gonna be easy. What is that one?
0.
0. Okay, let's keep moving to the left. The gravitational potential energy at the end. How high is it gonna be at the end?
2 meters.
2 meters. So how much gravitational potential energy does it have then? 200 joules, so 2 bars. Talk to me about the kinetic energy.
Force times. It's 620.
Where'd you come up with that?
Force times distance.
Force times distance. Okay, hold on. Let's back up for a second.
Oh, that's work. All right.
Well, let's do work first. I think we need to. So the work is the change in energy, which is force times distance. The student is applying a force of how much? 120 over a distance of
1 meter.
1 meter. So that means that she has done how much work? 120 joules of work. Why did they do that to us? That seems funny, doesn't it? I feel like there's something wrong with that. I feel like I missed something there. An applied force of 120 newtons upward with her hand. I think that's right.
No, it is.
Yeah.
And then
All right.
the kinetic.
So then let's talk about the kinetic energy here. So how much total energy do we have at the beginning?
560.
600. And then we're going to add 120. So that means we have 720 joules total. How much of that is potential?
200.
200. So how much do we have left? 520? The 20 is funny to me, but whatever.
Maybe you think we have bigger paper.
Yeah, but it started with this one.
Yeah.
I don't know. Whatever. It's all good. How are we doing, team? We okay?
Yeah.
One more? You've been sad because we haven't any springs yet.
Yeah, springs. No dark variation.
Yeah.
All right, let's talk about this one. A skateboarder, he's really cool. He's like, all right. On a skateboard is launched by a spring that's initially compressed to distance x as shown. Okay? His speed on the horizontal portion of the ramp is v, and then he rises to a height h. After leaving the ramp, we're going to ignore friction. Draw an energy bar chart for the Earth skateboard spring system. That's a lot of stuff. As he goes from the compressed spring at rest to when he reaches the height h. Put the 0 point for the gravitational potential energy at the initial height of the performer. Okay. That's a lot of stuff. Yeah?
Yeah.
Talk to me about the kind of energy he has at the beginning.
Spring potential.
Spring potential. How much is he going to have, Jonathan?
1,000,000.
Your name's not Jonathan.
Nick?
Pick a number.
2.
2. Okay.
I like that number.
How much gravitational potential energy does he have at the beginning?
0.
How much kinetic does he have at the beginning?
0.
Okay. All right, let's talk about the end. Does he have any kinetic energy at the end?
Yes.
Yep.
Oh wait.
That would be 0.
No.
Where's the end?
I thought
He rises to this height.
Yes.
So he stopped up there, didn't he? Yeah. How about spring potential energy? Any of it?
No.
No. Hey, is there any work been done? No force acting over a distance because the only force acting is gravity, but gravity's part of the system, right? So no work. So how much gravitational potential energy does he have then?
2.
Oh, that was easy. Boom.
I don't understand why there's no work being done.
Why? Tell me more.
There's no force from outside.
Because
There's outside God.
What's your question?
I don't understand how there's no work.
Because there's no outside force acting. Because it says draw an energy bar chart for the Earth skateboarder spring system. So if there was some other thing that was applying a force, then you would include some work, but there's no outside push or pull happening. What do you want to be pushing or pulling?
There's no friction. It's frictionless.
Oh, work is friction?
Friction can be work.
I'm just going through the forces. Like, there's no applied force. There's no.
Nobody's making it.
All right. Woo, we made it through with what, 12 minutes, 11 minutes to spare. This, yeah, that was, I'm going to tell you what that one was for. Hold on a second. Friends, let me tell you a couple things here. Quick. Henry said that there was one more chart. Yes, there is. Because I wanted you to be able to think about another idea, right? See if you can come up with something else. See if you can maybe draw a chart and then tell a story that would constitute that chart, right? That's another way to kind of think about it. So that's just that. I didn't give that one to you because there was a problem, just because there was like that opportunity for thinking. Is that fair? Okay. All right, so the sheet that I handed to you is not homework. It is not required, but it's kind of a fun problem to do. This is one of the things that I copied this as an orange one forever ago, probably because I got it in orange. When I was doing my student teaching, I got this from the guy that I worked with. I think he drew it. Anyway, so the story is that you've got a little box that's sitting way up here at point A. It's going to slide down this ramp, okay? It's got a mass of 2 kilograms. It's released from rest at point A. It's a frictionless track as shown below. It says to show all your work. I don't really care. I just think it's kind of a fun problem to do. So here it goes. It's going to go down here. Then it's going to go around this loop, right? And then it's going to go here, and then it's going to enter. It's going to enter this tube. It's a hollow, frictionless tube. It's going to go down, 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 down to the bottom, and then it's going to come out at E. Are you with me there? Okay. It happens to then go over a rough surface. Okay. So what's going to happen as it goes over the rough surface? It's going to friction, slow down, stuff, right? It's going to get to F, and then it's going to get into this. It's going to hit this ideal spring, and so it's going to go zoop, and it's got a spring constant of 20 newtons per meter. Yeah. And then after that, so the spring is going to compress, and then the spring is going to let it go again. And it's going to launch it, but it's going to go over the rough surface again, and then it's going to go back up the hollow frictionless tube. You with me there? Okay. Now, because it went through over the rough patch, that means that it's going to lose some energy, so it's not going to be able to make it all the way back up to the top. Are you with me there? Okay? So then the game is going to be, it's just going to bounce up and down and up and down and up and down. And question 11 says, exactly where will the mass come to rest? Okay? Just an opportunity. You do not have to do this problem, but I think it's kind of a fun one. Okay? So I'm going to let you guys work on it.
It's actually the test.
That's what you got. This is not the test, but that would have been funny, wouldn't it? Yeah, right?
Test.
Oh, rats. All right. Spend some time, work on this. I'll post some answers in a little bit. Sound good? All right.
No.
I thought it was like you